Hi everyone, my name is Alex, and today I'm going to present a workflow I've created for modeling the spread of invasive Burmese pythons using these data sources. I want to start with a brief introduction on invasions. The process is often simplified into these four distinct phases, and a lot of what we know about the invasion process is borrowed from earlier ecological theory. In particular, metapopulation ecology emphasizes a sort of reciprocal relationship between establishment and spread, where spatially structured populations are maintained by dispersal and gene flow between populations. Based on this, we know that the landscape's resistance to movement can affect dispersal success, as well as colonization and extinction rates, and the overall persistence of a species on the landscape. This is especially true considering that landscapes are rapidly changing, and a species' ability to disperse is affected by the type of habitat conversion or destruction underway. This correspondence between dispersal and population persistence has placed a lot of attention on landscape connectivity. So a lot of work has been done relating landscape characteristics to the connectivity of populations of a species or community, particularly through the development of such models as randomized shortest path, which allow the incorporation of path redundancy and movement through suboptimal matrix. But these models are, however, unable to capture the effects of matrix on mortality, which can alter dispersal success and survival rates. In an invasion context, these rates contribute to propagular pressure, a core component of invasion success. Ignoring propagular pressure when modeling invasions would seriously undermine predictions and any management relevant recommendations they provide. Getting at this issue, we can apply absorbing Markov chain theory to represent movements of transient states and mortality with absorbing states. This method has become more accessible through the introduction of SAMC, a temporally explicit framework which provides the ability to model dynamic connectivity, capture propagular pressure, parse multiple sources of mortality, and simultaneously predict species distributions. With that, I want to use a workflow I've developed to model the spread of Burmese pythons. Burmese pythons have had a tremendous success as an invader in South Florida, and since their establishment, there's been worry about pythons competing with native snakes, and their impacts have even been linked to declines in small mammals and altered disease dynamics with their prey and other native snakes. While pythons are hypothesized to spread throughout peninsular Florida, the factors which promote or prevent further establishment are largely unknown. In this conceptual diagram, I've laid out a few factors which I hypothesize to influence dispersal and persistence of pythons. For factors affecting persistence, we have cold mortality due to seasonal climate, road mortality from vehicle strikes, and mortality from deliberate removal programs. And for factors affecting dispersal, we have simply habitat or land use conversion, which can affect habitat suitability and the persistence of habitat corridors. For instance, the Florida Wildlife Corridor, which stretches in the Everglades to North Florida. And the idea here is that we can represent these factors as resistance and absorption layers to directly evaluate their contribution to the spread of pythons. Now I want to work through some of the methods for this model, beginning with the resistance layer. For this, I'm treating landscape resistance as the inverse of habitat suitability, often referred to as conductance. And to create this layer, I began with a habitat suitability model for pythons using an extensive presence-only dataset provided by the Florida Fish and Wildlife Conservation Commission. For predictive variables, I used the National Land Cover Database with published reclassification scheme, as well as human modification of terrestrial systems dataset. I fitted this model using a Maxent algorithm and obtained predictions from the model to calculate resistance. Now moving on to the absorption portion of the project. To create my absorption layers, I started establishing a background mortality rate to which all additional mortality sources would be adjusted. To do this, I began with daily mortality, using this formula to back calculate daily mortality from an estimate of adult annual survivorship from the literature of 90%. Using this estimate, which is essentially mortality per time step in my model, I then focused on dispersal-related mortality, or the mortality per spatial unit. Following the approach of Marks et al. For Florida panthers, I began by simulating dispersal in a homogeneous landscape under various mortality scenarios, which were informed by the previous daily mortality rate, essentially adding and subtracting from that previous estimate. I then selected the mortality risk scenario, which yielded an estimate of daily dispersal that matched the mean max dispersal from the literature, and that's 180 meters. See here. So this would serve as background mortality rate. Now moving on to my hypothesized absorption sources. First, road mortality. To estimate the spatial pattern of road mortality, I used data from EdMaps, which features a variable that indicated if snakes were found dead or alive. I then filtered those data to only observations within 5 kilometers of roads. I then fit a relative risk model or log binomial model to the data with road densities as a covariate, calculated at scales from 360 meters to 4 kilometers. I then compared the effects of roads at different scales by ranking the performance of models and found that the top 3 models had similar support. So instead of taking predictions from one model, I averaged across the whole candidate set to obtain a model average layer of relative risk of mortality from roads. Now, switching to the Python removals program, this one's pretty simple. I obtained data from Florida FWCC's removal program, which has 2 categories of paid contractors who remove snakes. I then fit a smooth KDE to the data to get a more broad sense of where those removal efforts are being focused. And I did this without using roads as a covariate because the previous method really got at those mortality around roads. Now to the last step for the absorption layers. This one is cold mortality. It's by far the most intensive portion of the project. So I'll start off with just an overview. Along with the help of Dave Lingus, who's working on some really cool microclimate work, we got thousands of climate time series from weather stations across the southeastern United States, and then combine that with microhabitat information, including things like leaf area index, topography, soils, and generated a microclimate model of Florida. We were able to then feed this into a model of Python body temperature to get the spatial probability of cold mortality. Now, to go to microclimate portion of this, we collected data from a network of weather stations and fed these data into a microclimate model using the NicheMapR microglobal function and created point-based hourly predictions of near-surface microclimate from a meter below ground to 10 centimeters above ground. Then splined these time series predictions into a spatially continuous layer of climate in discrete time for 108 days throughout the year. We chose not to use an entire year because just for temperature alone, this generated 4,300 raster layers. So we tried to keep the computational limits reasonable for other users. Now on to the Python body temperature. So to do this, we use the dynamic energy budget model for ectotherms available in NicheMapR. For this model, it can get really complex really fast, so I provided about 25 parameters for Pythons, including thermoregulatory behaviors, allowing burrow use, climbing, specifying activity phases, and retreat use. The output from this model is similar to the previous step, in which we need to spline these layers together to get a statewide Python body temperature time series. And to calculate cold mortality from this time series, we consider mortality to result when a Python's internal body temperature drops below the published CT-min of 8 degrees for more than 6 continuous hours. So this yields a final layer, a single layer, of the probability of Python cold mortality. It's in here. So now we can actually get onto the connectivity model. Now we need to specify the source populations or propagules of Pythons in order to simulate spread. To do so, I used a point process model to predict the relative prevalence of Pythons in South Florida. This will represent the propagule pressure of Pythons in a simulation. Now, the actual scenario of this simulation is kind of nuanced. Specifically, we're simulating the spread of Pythons out of the Everglades National Park from 2020 to 2050. And for those of you who have used SAMC, the model performs best when you're simulating dispersal out of a discrete location with a defined boundary. So I masked the predictions of Python prevalence to the Everglades National Park's boundary to represent spread out of the park. I'm also considering a nearby wildlife refuge, the Loxahatchee, as a site of potential invasion because in recent news they found their first adult python there and they're worried that establishment will soon follow. So I wanted to model spread to the Loxahatchee as well. Now moving into the predictions of this model, starting with estimated mortality from the absorption layers. I've arranged mortality from left to right in order of the greatest effect, and the color scheme here represents mortality as a good thing. So cool areas have high mortality, hot areas have lower mortality. And you'll notice in our road mortality section, the Miami metro area has really high mortality, as well as some of the major roads across South Florida. The removal mortality is most obvious in South Florida, where all of those removal efforts are being concentrated. And then obviously with cold mortality, we have the highest rates in the northernmost latitude. Now looking to survival, which is interpreted as the number of time steps until absorption, with a time step being equal to 2 days. We see extremes here at the northernmost extent, where survival is low due to cold mortality, and down at the southern extent, survival is low due to the combination of roads and removals. And then we have relatively high survival there in the middle. Now on to the predicted occupancy. This is a kind of a temporal visualization of occupancy where I collapsed hundreds of layers of probabilistic occupancy estimates into a duration of probable occupancy. So these would be the number of years this pixel has a predicted occupancy greater than 50%. Now on to simulating dispersal between the Everglades and the Loxahatchee. Now we can look at a metric equivalent to what you'd get from a circuit theory approach, interpreted as flow or the centrality of flow. On the left, it is an example of the kinds of data product that we'd share with our partners at FWCC, an interactive leaflet map. And on the right is a map I've shown of connectivity with 2 additional patch areas highlighted here. Under those polygons, there's a bright, hot red indication of high visitation at this site. So our model might actually be indicating that these patches could be stepping stones between the 2 main nodes of the Everglades and the Loxahatchee. And I looked into these areas, and they've actually been getting a lot of Python activity relative to adjacent areas, which I think is really interesting. Now we can compare these results from our model to what we'd actually get from a circuit theory approach. And interestingly, circuit theory is actually a limiting scenario of SAMC in which the only absorption on the grid is at the destination node. So we can see, relative to a model with absorption on the right, circuit theory predicts no flow in urban and suburban regions of South Miami and highly centralized corridors between nodes. Our model shows much less deterministic flow with some diffusion north of our starting node and some flow into southern Miami, resulting in absorption and ultimately a less centralized corridor toward Loxahatchee. And these results make a lot of sense when you consider that Pythons have been on this landscape for decades, but only recently has a single Python showed up at the Loxahatchee. So now I want to discuss a little bit about this model. First, its potential to improve the realism of predictions by evaluating multiple facets of invasions, not just dispersal and the resistance of the landscape. But this could actually pose circuit theory as a sort of null model in which the spread has no effect by mortality. Now, some of the considerations of this model include that mortality data are often really rare or spatially complete. And obtaining mortality data likely requires expert elicitation, and in this case, estimating our cold mortality was really challenging. You could take this approach top-down by designing thermal experiments to determine thermal limits of a species, or bottom-up, which is the method here, by estimating microclimate and then body temperature. But this is really costly computationally. Luckily, we have access to supercomputing processes, but not everyone has those. And then lastly, potential connectivity requires validation. Often, after models like these are created, they then use telemetry data to actually validate this approach or look for evidence of post-dispersal reproduction or even genetic data. So future work is going to have to validate these predictions, but we believe that this model can move us towards incorporating a more biologically meaningful process into invasion modeling. I'd like to acknowledge the Robin Nadeau Graduate Award, as well as the Preeminence Fellowship here at the University of Florida, and our funding partners, the USGS and SCASC.
And I want to thank you all for coming to my talk.